Beautiful. Hey, so today, guys, what we're going to do is we are going to take everything that you've learned up until this point. And guys, notice we've spent a lot of time on this. We're going to take everything that you've learned as you've learned to draw Lewis dot structures, and we're going to make these things literally jump off of the page, and we're going to make them three-dimensional. So guys, the idea is this. Up until now, we've been drawing these Lewis dot structures. And actually, Zach, I didn't pick the one that you particularly mentioned when we were grading homework. But guys, at this point, you should be, and apparently you are, based upon the questions that you ask and the fact that most of you said, yeah, I'm good on the homework. Guys, we together are at the point where we're getting good at drawing these Lewis dot structures. But guys, hopefully as you've been grading homework, as we've been talking about this idea that up and down and left and right really don't matter. Guys, hopefully you're coming to this idea that these things have limitations, that they're really good at describing where bonds are and the type of bonds there are. But guys, what they don't do is tell us what these look like three-dimensionally. As Zach pointed out, they don't even really tell us symmetry very well. And guys, that's going to be a really big idea moving into January, is symmetry. So what we need to do is we need to make these three-dimensional. So guys, do this with me. Grab your note sheet, flip it front and back, and just sort of get a general sense of what you've got in front of you. So guys, here's what we're going to do. Flipping to the front of your notes page, you'll notice, guys, that there are some terms, there's a structure to this, and it's obviously formatted like class notes. So guys, what we're going to do today to help you take these flat, lifeless Lewis dot structures and make them three-dimensionally meaningful, guys, is first of all, we've got to define some terms. Scratch these down with me. Along the way, we're going to talk about whether or not you understand what you're learning on this. But then, guys, once we get into this, the big idea is going to be electron domains. So guys, take that idea and now flip this over onto the back. Guys, allow your eye to scan down this paper, and you'll notice that there is a repetitious organization to it. That there's a heading that is in bold, and then there is the place for you to write down an angle and a name, and then there's a table. But guys, notice the way that this is organized given the headings that are in bold. The way we're going to organize this information is by domains. So we've got 4 domains, 3 domains, and 2 domains. So guys, the bottom line is this. On the front of this, we're going to learn about domains. And then on the back, we're going to use these domains to organize what we're learning. So guys, as we transition then, this is where we're at and this is where we're going, and do not write any of this down. But guys, here's where we are. At this point, we've gotten really good at drawing Lewis dot structures, these two-dimensional representations of molecules. And guys, these are really good at what they're good at. They're really good at telling us the order that things bond. They're really good at telling us the types of bonds that form. But guys, what they don't do is tell us about three dimensions. And that's what we're doing today. We're going to push our study of these molecules into 3 dimensions. But before we do, we've got to define some terms, and that term is electron domain. And so guys, this is where you want to start taking notes. You'll notice that there's a place for you to do this right on the front of your paper. And guys, let's pick up here and get started. So let me define it for you and then we'll talk about it. So guys, fundamentally, this is it. An electron domain is simply the space that electrons occupy around the nucleus of an atom. Before you go, grab this. So guys, fundamentally, an electron domain is just a space that electrons occupy around the nucleus of the atom. Now guys, here's the trick. Make this connection with me. This is not a new idea. You've just never known them by this name. Because guys, when you were drawing your Lewis dot structures, remember that I had you count shared and lone pairs? Guys, without knowing it, when you were counting shared and lone pairs, what you were actually doing is counting domains. So guys, the domains are the shared and lone pairs. Now guys, along the way, what you're going to find out, and this is already in your notes, so you don't need to write this down, there are two types of domains. There are what are called bonding domains, and there are what are called non-bonding domains. So guys, let me define these for you, and you'll notice this now fits into your notes. So guys, the bonding domains are the shared pairs of electrons. You'll notice that there's a tick mark, bonding domains. Those are the shared pairs. And then guys, the and you don't need to write this down. I'll show you what this means. Any type of bond counts as one domain. And I know that seems muddled, but you'll understand in a second. And then we'll make sure. And then guys, the non-bonding domains are the lone pairs. And you'll notice it says non-bonding domains. And then there's a place for you to write in that those are the lone pairs. So guys, fundamentally, this is what this means. A domain is simply a place that we find electrons. Could be a single bond, a double bond, a triple bond, or a lone pair. They're all domains. So guys, what I'm going to encourage you to do is write these in. Draw the domains, and you'll notice there's a place for you to do this in your notes. So as you do these, each of these is a domain. A lone pair is a domain, a single bond is a domain, a double bond is a domain, and a triple bond is also a domain. They all count as one. Because guys, it doesn't matter how many electrons are in the domain, it's still one place that electrons occupy. So guys, what we need to do is we need to make sure that you understand what this means before we move forward. So once you're all caught up with me, we're going to sort of stress test your understanding before we get moving. You guys okay? You all caught up? Okay, so guys, please do not draw this. But guys, this is the molecule that you have to memorize. And we're going to use it as an example so that we can figure out whether or not you're comfortable with identifying domains. Because guys, this is something you've got to be able to do. So guys, looking at that carbon right there, here's the question. How many domains are on that carbon? I want to give you a second to think about it. How many domains are on that carbon? So guys, I really want you to vote with your fingers. How many domains are on that carbon? I'm seeing some. Max, what do you think? Ryan's got 4. Max, what do you think? How many domains are on that carbon? You got 4. Is everybody comfortable with 4? Does that make sense? So guys, we've got 4 domains, single bond, single bond, single bond, single bond. That's 4 domains. But guys, this gets a little trickier when we go over there. How many domains are on that carbon? Vote with your fingers. We got 4. We got 4. Millie, what do you think? We got 4. Zach is voting 3. Mikkel is voting 3. Parker, what do you got? 3 or 4? We got 4. Guys, we got a toss up here, right? We've got some that are voting 3. We've got some that are voting 4. But guys, if you look at your notes, remember what you drew in. A double bond counts as one domain. And so guys, the idea is this. Here's a domain. That's a space where there are electrons. Here's a domain. That's a space where there's electrons. And guys, here is another domain. There's more electrons in that domain, but guys, it's still just one domain. So are you comfortable that the answer is 3? Do you understand now better about what? Any questions on that? Is that okay? Max, you okay? Okay, so guys, let's do another one then. What about this? Oops. What about that oxygen right there? Guys, how many domains? Give me fingers. How many domains? Aline, what do you think? Yeah? Fingers? Josue, what do you got? How many domains? 2? We got 2, we got 4, we got, what are you going with, Grayson? 4, and we got 2. So guys, we've got a division here. And again, I'm choosing these examples to bring up these differences. So guys, let's look. For those of you that are voting 2, I'm guessing that you're voting those 2 domains because those are bonds. But guys, are those the only electrons around the oxygen? There's electrons here and there are electrons there. They're not involved in bonds, but there's still electrons around the atom. So this is a domain and that is also a domain, and that then gives us 4 domains. Questions on that? You okay? If you voted 2, do you now see why it's 4? Okay, so guys, at this point, you've seen all the crazy rules, so let's do that oxygen, and at this point, this should all come together. Show me. Jordan, what do you got? Yeah? David? How many domains? Let's take a look. Where are we at? Izzy, what do you got? 3? Guys, do you see that it's 3? We have 3 domains. We've got a double bond, we've got an unbonded pair, we've got an unbonded pair, so this would be 3 domains. So guys, the question then becomes, why do we care about domains? And the answer is simply this. These domains push on each other. They're all full of electrons, and they push on each other, and when they push on each other, that's what gives these molecules their 3-dimensional shapes. So guys, being able to count domains is critical because that determines what these molecules look like. So again, we've got 4, we've got 3, we've got 4, and we've got 3. Guys, questions there before we move forward because this is an important skill. Guys, okay? And we'll practice more with it, but that's the idea. Anything now? Okay. So guys, let's continue on then. So now that we together understand maybe what these domains are, guys, continuing on, we now need to talk about something called Vesper Theory. You'll notice this is in your notes. Guys, scratch this down. So here's the idea. Now that we understand this idea of what domains are, we now need to talk about what they do. And the answer is that they Vesper. And guys, this is obviously an acronym, and it stands for the valence shell electron pair repulsion theory. But guys, if you carefully think about what you're writing down as you write it down, as you write this down, you should kind of be saying to yourself, yeah, I kind of already knew that. Because guys, when we talk about valence shell electron pairs, we're talking about domains. But we also know that electrons are negative, and as a result, they repel each other. So guys, all this simply says is that electron domains repel each other. And as a result, this repulsion causes them to get as far apart as possible. And guys, that's an important idea. They are trying to get as far apart as they possibly can. So guys, we've got one more thing to talk about relative to these domains. Then we're going to have set the stage, and we're going to be ready to actually dig into this theory and actually talk about what these molecules actually look like 3-dimensionally. It's good stuff. So guys, as you're scratching this down, let's review really quickly. So the first thing we know is this. There are these spaces where we find electrons. We call them domains. But guys, there can be any number of electrons in these domains. Single bond, 1 domain. Double bond, 1 domain. Triple bond, 1 domain. Unbonded pair of electrons, still just 1 domain. And then guys, we also now know that these domains push on each other, and when they do, they spread out as much as they possibly can. So guys, the only thing we need to talk about now is this. These domains don't look the same. And I'm going to have you draw these just to sort of drive home the idea. So guys, not all these electron domains are the same size or the same shape. So guys, let's talk about bonded electron domains first. Bonded electron domains are long and skinny. You'll notice there's a place to scratch this down. Bonded electron domains are long and skinny. The reason that they're long and skinny is they're being stretched by the pull of 2 nuclei. So guys, literally that shared pair of electrons that they're fighting over in this covalent bond, a bonded domain is long and thin. So guys, what does a cloud of long, thin electrons look like? Like this. I would encourage you to scratch this down. Maybe you draw it, well, down below or off to the right. It's up to you. But guys, the idea is that we've got, in a bond, we've got 2 nuclei pulling on these electrons. And because that's true, the cloud gets stretched out. So this is what a stretched out electron cloud looks like. And then, guys, non-bonded electron domains. It's actually quite different. Non-bonded electron domains are short and fat. Why are they short and fat? They're short and fat because they're only being pulled on by one nuclei. So guys, once you're done drawing what that looks like, we'll talk about it for a second. We'll get all your questions gathered together. And then guys, we're going to flip this over and we're going to start doing some thinking. So guys, this is what short and fat looks like. That is literally what a non-bonded electron domain looks like. Yeah, Zach. Like this sort of shape? Yeah, the reason is actually because so think about what this normally would look like, right? We're talking about valence electrons. So you've got this S shape and you've got this P shape, right? And so when you start to pull on those S and P orbitals, they either start as a sphere or they start as dumbbells. But then what happens is as the nucleus pulls on that, they kind of slump a little bit. And as they slump, this is the shape they fall into. So guys, the idea is this, and then we're going to get going. So shared and bonded domains and their shapes. Imagine this rubber band represents a cloud of electrons or a domain. Now guys, here's the idea. If my fingers represent the nuclei of atoms, if we've got a bond, these things are pulling in both directions. So we've got a nuclei pulling in both directions, and that makes the domain long and thin. Now guys, if we're only pulling in one direction, then, and Zach, this is kind of what I was trying to explain, and it's hard to do, but the idea is that it kind of slumps, right? That orbital slumps because it's only being pulled on by one nuclei, and it becomes that shape, short and fat. So, guys, let's call time out for a minute, and then we're going to get into the thinking part of this. So here's where we are. Domains are spaces that contain electrons. Could be an unbonded pair, single, double, triple bond, doesn't matter. We know the domains push on each other. And then finally, we know that bonding domains are long and thin, and unbonded domains are short and fat. Questions? You guys okay? Okay. So, guys, take your paper, flip it over. And this is where this begins to get a little bit interesting. So guys, let me set the stage for you. Consider, for example, a water molecule. How many domains are on this oxygen in the water molecule? How many domains? 4. We've got single bond, unbonded, unbonded. We've got 4 domains. But now guys, this. What do the bonded domains actually look like? Long and thin or short and fat? Long and thin, short and fat. The bonded ones. They are long and thin. So guys, these domains are long and thin. What about the unbonded domains? Well guys, these two are short and fat. And what does that do to the molecule? And guys, the answer is this. This is what it does to the molecule. These unbonded electron domains, which don't even show up in these models, but we actually have pretty little purple things that we can stick on here. Guys, these unbonded electron domains, because they're short and fat, push the bonded domains away, and it causes a water molecule to bend. And that's actually where we're headed with this. By knowing the number of bonded and unbonded domains, we can figure out the shapes of these molecules by simply drawing on the idea that these domains push on each other. Now guys, in order to organize that thinking, allow your eyes again, now that you understand what domains are, to scan down this paper. Guys, notice how we're going to organize this. We're going to first of all talk about the atoms that have 4 domains. Then we're going to talk about the molecules that have atoms with 3 domains, then the ones that have 2 domains. And guys, when we're done with that, we're going to quickly flip to your homework, and you really should get your homework done today. You guys ready to get this organized? Okay. So guys, in order to do that, I have a question for you that I do not ask hypothetically. Guys, do not write this down, but you will write down the answer. And guys, the question is this. When 4 objects surround a central point, 4 objects around a central point in 3-dimensional space, Guys, what are the angles that are created if these points are as far apart as possible? Let's take a look. So, and I love that you guys have an immediate answer. So guys, here's our central point, here's our space, and if I put a point there, how can I get the second point as far apart from that as I can? Put it on the other side. But then guys, we need 2 more points, and when I spread these points out, these are now spread out as far as we possibly can, right? And now when I connect the dots, what are the angles? 90 degrees. But guys, the answer to this question is not 90 degrees. That's the problem. This is 2-dimensional, and guys, the answer has to be 3-dimensional. So guys, allow me with you to make this 3D and make a horrible mess. So guys, the first question is this. What does this have to do with the question on the board? Good. It's 3D and 4 points. So 1, 2, 3, 4. Now guys, where's the central point? It's going to be up here in the middle. But guys, one more interesting question for you. Notice the question says spread apart as far as possible. Guys, when I made this, and I just made it the other day, guys, when I made this, what did I do that allows me to say with confidence these points are as far apart as possible? Say it again. What about the outer edges? They're all the same length. Guys, literally what I did is I just tapped down a fistful of straws and I cut them all at the same length. And because the straws are the same length, these points are as far apart from each other as they possibly can be. So guys, we've already established that 90 degrees is not the answer to the question. So what is the answer to the question? Well guys, we're going to let nature answer the question. So what we're going to do is we are going to connect these 4 points with a substance that is so weak, actually bubble juice, that it's going to try to connect these points in the easiest possible way that it can, because it's so weak that it's going to try to maximize its strength and become as stable as it possibly can. And guys, when it does that, you can see that that is not a you can see that that's not a 90-degree angle. So guys, let's take a look. So here we've got our 4. Can you see the center point in the middle? It's really fragile, so I don't want to... Oh, shoot. Can you see that center point? Can you see the angle? So... You guys know you can actually get a PhD in the math of bubbles? Yeah, some of the most fascinating math that they're doing right now is describing the math of bubbles. It's really cool. So guys, I'm going to hold this here and not breathe on it because it pops. Is that angle greater or less than 90 degrees in there? It's greater than 90 degrees. Does anyone happen to know what it is? It's actually not 120. Guys, interestingly, it's 109.5 degrees. And that's an angle that you need to know. So guys, please write that down under where it says 4 domains. Because guys, understand, we're really talking about domains, right? And so when we spread 4 domains out into 3-dimensional space, it's not a 90-degree angle. It is a 109.5 degree angle. But now guys, we need to name this thing. So these are our 4 points spread out. Again, these are 109.5 degree angles. But guys, in geometry, when we've got 4 points, we call that quad or tetra. And we use tetra, and so the name of this structure is what we call tetrahedral. All right, so guys, this then is where we're at. If we've got 4 domains spread out in 3-dimensional space, that forms 109-degree angles, and we call that tetrahedral. So guys, now I need to catch up with you, and now we're on the same table. So guys, what we're going to do now is we're going to talk about molecules that have 4 domains. Therefore, they start looking like tetrahedrons. And guys, the 4 that we are going to do are these. Write them down with me. We're going to do CH4, we're going to do NH3, we're going to do H2O, and we're going to do HF. Now guys, I chose these 4 molecules and put them in this order for a reason that you're going to see. But you also need to understand these are molecules that you've already drawn the Lewis dot structures for. As a matter of fact, 3 of the 4 are right here. CH4, NH3, and HF were the first 3 that you did on the previous homework assignment. So guys, rather than have you sort through drawing these, let me just do them for you. So guys, draw their Lewis dot structures in the spaces provided, and I would encourage you to write them the way that I did. Did you guys like the bubble thing?
Yeah.
That's pretty good stuff.
Where do you find that?
Find it. Like the idea of it? I don't know. It may have actually been my idea, but there's really no new ideas in teaching, so I'm sure I lifted it from somebody. They say that good teachers are also great thieves. We steal stuff from each other. All right, so guys, do this with me. Once you've got these drawn, allow your eye to scan through your Lewis dot structures and ask yourself this question. How many domains are around the central atom in each of these molecules? So guys, how many domains on the carbon? 4. Nitrogen? 4. Oxygen? 4. Fluorine? 4. Guys, that's the point. All of these have 4 domains around the central atom. But guys, what you're going to find out is they don't look anything alike. So they all have 4 domains, so they all start with the tetrahedral domain geometry. But guys, what you're going to find out is they don't look the same because not all the domains are bonding in all 4 molecules. So let's do this. Guys, going up to CH4, how many of those 4 domains are bonding? All of them. How many of them are non-bonding? Well, none of them. And guys, we've already talked about this. That looks like this. This is methane. This is actually natural gas. CH4 is the stuff that we burn in our Bunsen burners and our furnaces and stoves at home. Guys, this is the molecule. And we can clearly see these 4 points all spread out into 109.5 degree angles. And guys, this molecule is called tetrahedral. All the domains are involved in bonding, so the domain and molecular geometries are the same, and that's tetrahedral. So now guys, let's go down to the next one. Looking at NH3, how many of these 4 domains are involved in bonds? 3 of them. How many are not bonding? 1. So now guys, let's talk. Let me show you what this looks like. So guys, this is an NH3 molecule. And you can see that it doesn't look like CH4. Guys, what's missing from the picture? What's up here that we don't see? The unbonded pair of electrons. Here, I can even put them in because I've got this. So guys, we've got a big, fat, unbonded pair of electrons up here, but we don't represent it in the structure. But guys, what is this? Watch my fingers. What is this big, fat, unbonded pair of electrons doing? It's pushing. It's literally pushing these hydrogens down. And when it pushes down, what happens to this angle? Does it get bigger or smaller? It gets smaller. Guys, you don't need to know how much smaller. The answer is actually 2.5 degrees, but you don't need to know that. All that you need to know is that the angle is less than 109.5 degrees. Again, it used to be that you had to know the angle. It's actually 107, but they wrote it out of the AP curriculum, so I'm not going to teach them to you. So guys, now we need to name this thing. Is this a tetrahedron? No. So let's name it. Guys, what's the geometry word for 3? Tri. And then, would you believe that it kind of looks like a pyramid? Yeah, that's where the name comes from. We actually call it trigonal pyramid. All right. So now, guys, let's take the next step down. And let's go down to water. Guys, looking at H2O, how many of the domains on that oxygen are involved in bonding? 2. How many are not? You're starting to see the pattern, right? How many are not involved in bonding? Well, also 2. Didn't I have a water molecule? Where did it go? What's that? Oh, there they are. All right. There we go. All right, so guys, now we need to name this. So this is our water molecule. What's missing from the picture? 2 big unbonded pairs of electrons. That pushes down even more, and it makes this angle even smaller. How much smaller? Another 2.5 degrees, but you don't need to know that. You just need to know that it's less than 109.5. And then, guys, we got to name this thing. Guesses? Well, not triangle. We already got trigonal pyramid. Somebody knew it. Did you know that? It's actually, guys, it's kind of anticlimactic. We just call it bent. I know. But it looks bent, so at least it's realistic. All right, so guys, we got one more to go. And the last one that we need to talk about is HF, where we've got 1 bonding and 3 unbonded domains. And guys, this looks like this. There's our H, there's our F, 3 big unbonded pairs of electrons hanging off to the side. What do those 3 unbonded pairs of electrons do to the angle? Nothing, because there isn't an angle. Guys, in order for there to be an angle, there has to be 3 points. 2 points don't define an angle. What do they define? A line. And so, guys, we say that the angle is undefined, and the name of this is what we call straight. It's a straight line. So, guys, there you have it. What do these all have in common? Same domain geometry, 4 domains, tetrahedral. If all of the domains are bonding, the molecule's tetrahedral. If 3 of them are bonding, trigonal pyramid. If 2 are bonding, it's bent. And if 1 is bonding, it's straight. You guys get the idea? Now that you understand the pattern, we can do this now for 3 and 2 domained molecules. So guys, let's go on and let's ask the same question about 3 points. So guys, again, you're not writing this down, but here we go. So guys, same question. 3 points, 3-dimensional space, spread out as much as we possibly can. What are the angles? Well, guys, here we go. If I put a point there, and if I put a point there, and if I put a point there, these are now spread out as much as they possibly can be. And when I connect the lines, what are all the angles? 120 degrees. 360 divided by 3, 120 degrees. But now, guys, let's make it 3-dimensional. Done. Guys, it does not matter if we do this in 2 or 3 dimensions. We can't get these any further apart. We could lift them and push them in and out of the plane of the screen. And guys, this is it. This is as far apart as they possibly can get. So guys, they spread out into 120 degree angles. So now, guys, we need to name this thing. And again, we've already established that the word for 3 is tri. But not quite. Here's the other thing we pick up on is they are all in the same plane. So we call this trigonal planar. So now, guys, switching to our table. Switching to our table, we're going to look at these 2 examples. CH2O is the very first molecule that we did in today's homework. There's a method to our madness. And then, guys, NO2 ion, we've actually done twice now. So let me give you the structures. So guys, this is a good time once you're done drawing these to slow down for a second just to drive home the organizational idea here. So guys, let's be really sure we're sure, because when we played this game earlier in the day, there was some confusion. Guys, how many domains are on that carbon? 3. Single bond, double bond. How many domains are on the nitrogen? Also 3. Single bond, double bond, unbonded pair of electrons. They all have 3. So guys, let's do this. On the CH2O, there are 3 domains. They are all bonding domains, so we have no non-bonding domains. Guys, the molecule looks like this. Does trigonal planar now make sense? We've got the double bonded oxygen, we've got the hydrogens. You can see 3 points. They're all in the same plane. Guys, what are these angles? 120-degree angles. And guys, what is the name of this? It's trigonal planar. So guys, this is a 120-degree angle trigonal planar molecule. Cole, that's brilliant. And the answer is actually it does a little bit. The reason is because there's actually 4 electrons in here instead of 2. So it does open that angle up a little bit. It's like 1/3 of a degree. And so understand that when you get into, if you do chemistry, when you get into your sophomore year in chem, you'll end up taking this class, which is organic chemistry, and then you'll learn the specifics of all those little angles, but for here it's just close enough. Yeah, but that's a great observation. So, guys, let's now go to NO2. Again, guys, we've got a molecule with 3 domains on it, but now, guys, we've only got 2 bonding domains. We now have a domain that is not involved in bonding. There's one of them. But guys, let's remind ourselves what that unbonded domain looks like. So guys, here's the molecule. Double bond on the left, single bond on the right. Looks like this. What's up here? That big, fat, unbonded pair of electrons. And just like before, it pushes. So what happens to that angle? It gets smaller. Smaller than what? Not 109.5. Smaller than 120. And again, guys, hugely disappointing, but what are we going to call this guy? Also bent. Yeah, it's bent as well. So now, guys, typically at this point, somebody says, hey, wait a minute. Why didn't you give us a 3rd example of a molecule that has 1 bonding and 2 non-bonding domains? Guys, why didn't I put that? And the reason is because I didn't need to. Because anytime you've got 1 bonding domain, it's always an undefined angle and a straight geometry, because there is no angle for there to be. So guys, they exist. I just didn't put it because anytime there's 1 bonding domain, the angle's always undefined and the shape is always straight. So I just didn't put it just to save space. You guys good? 1 more to go. And then, guys, oh, wow, we're killing it. You guys are going to get your homework done. Let me do this and this and this. All right, guys, same question. 2 domains. So, guys, if we're spreading 2 domains out in 3-dimensional space, we go like this. What's the angle? 180 degrees. Can it get any better in 3-dimensional space? No. So guys, the angle is 180 degrees. So now we need to name it. And guys, all 3 of these points are on the same line. That's it. It is a linear domain geometry. Be careful with straight. Straight and linear are not the same thing. Linear is 3 points, 180 degree angle. Straight is 2 points and no angle. So don't confuse those two. So guys, the one that we're going to look at is carbon dioxide that looks like this. So bonding and non-bonding domains on that central carbon. There's 2 bonding domains. Again, the central carbon, not the oxygens. The central carbon, 2 bonding domains, no non-bonding domains. And guys, this is all about linear. Here's what it looks like. You've got the carbon with the oxygens on both sides. You can see the 180-degree angle. You can see that this is all in a line. It's linear. So guys, classic 180-degree linear geometry. Now again, I did not put an example where there's 1 bonding and 1 non-bonding domain. You'll see them in homework. But again, guys, anytime you have 1 bonding domain, there is no angle and the geometry is straight. Yeah?
But if there's 1 bonded and like 4 or 3 unbonded, would it push it away from stuff?
So the example that you just mentioned, Zach, is this. You've got 1 bonded and 3 unbonded domains. And so, yeah, the domains certainly do push, the unbonded domains push on each other, but understand it doesn't affect anything with this other atom because there's nothing to bend or twist. Is that okay? Okay. So, guys, we're done. The question then becomes, what are we going to do with this? So guys, grab your homework packet if you would, please. Turn to the homework that we just turned in today, assignment number 4. And guys, looking with me at your answers to assignment number 4, you've got this. Here's what you're going to do. Guys, looking at assignment number 5, and can you just flip over with me really quickly? Do you see that the molecules are all the same? They're all the same. So now, guys, switching back to your answers for assignment number 4, here's what you're going to do. You are going to ignore, don't cross them out, but guys, you're going to ignore the shared and lone pairs, and you're going to identify the domain geometry, the molecular geometry, and the angle. So the question becomes, how are you going to do that? So guys, let me lend some guidance. So these are the answers, these are the instructions for assignment 5. Draw the Lewis dot structures. You're already done. That was the homework we turned in today. Then it says identify the domain and molecular geometries and determine the angle. Guys, don't write this down, but let me offer you a problem-solving strategy. The first thing that you want to do is count the total domains on the central atom. That will be 4 or 3 or 2. Guys, that will then place you in one of these 3 tables, 4 and 3 and 2. Guys, that will then tell you the domain geometry of the molecule. Then at that point, you're going to count the number of bonding domains. That will tell you which line of the particular chart you're on, and this will then give you what we call the molecular geometry and the angle. So guys, here's what I'd like to do. I would like to do a selection of these with you. So as we do these together, we're going to do 20% of your homework together right now. So guys, do these with me, starting with number 1. This is the process. So guys, how many domains are on that central carbon?
3.
There are 3. So what is the domain geometry? It is trigonal planar because there are 3 domains. Now, guys, we got to figure out the molecular geometry and the angle. So now we need to ask ourselves this. How many of those domains are bonding domains? All of them. So, guys, that puts us on the top line of that chart. And that means that the molecular geometry is also trigonal planar, and the angle is 120 degrees. That's it. Those 3 for every single one. So guys, let's do number 2. Looking at number 2, and please ask questions as we go. Guys, looking at number 2, how many domains are on the silicon? 2. So what does that make the domain geometry? We're in the bottom table. What's the domain geometry? So guys, 2 domains. Find 2 domains, 4 and 3 and 2, bottom chart, 2 domains, linear. So on this one, the domain geometry would be linear. Then we need the molecular geometry. So what's the molecular geometry if both of those domains are bonding domains? Also linear. So guys, you can just put tick marks, also linear. And then we need the angle, and the angle will be 180 degrees. Okay, then guys, this. Looking at the next molecule, number 3, it's the one you have to memorize. How do you know the central atom? It's underlined in the assignment, and it's bolded in the answers. We're going to leave it at that. Now guys, this. Let's do number 7 together. So guys, looking at number 7, we've got N2. Which one is the central atom? Either one, but you got to pick. So guys, let's say, for example, we choose the nitrogen on the right. How many domains are on that nitrogen? 2. So the domain geometry is linear. Now guys, we need to know the molecular geometry. How many bonding domains are there? There's 1. And you'll notice that your table doesn't include that, because anytime there's 1 bonding domain, so the molecular geometry is straight, and then the angle is undefined. And then guys, I'd like to do one more with you, if I may. The last one that I'd like to look at with you is the bottom one, PF3. How many domains are on the phosphorus? Number 12. How many domains are on the P? 4. So guys, there's 4 domains on the phosphorus. So the domain geometry is tetrahedral. And guys, how many of those domains are bonding domains? 3. So looking at our table then, we're down where there are 3 bonding domains. That makes the molecular geometry trigonal pyramid. And guys, be careful with how you abbreviate if you do. You can't just put trig and then P, because that could also be trigonal planar. Trigonal pyramid and trigonal planar, you have to write out a little bit more. And then guys, if it's trigonal pyramid, the angle is, less than, the angle is less than 109.5 degrees. So guys, anything you need clarification on? You okay? Okay, so this is what we're going to do for the rest of the day. You should get this done. We will grade this on Wednesday. That is the last thing to go in your grade. Then guys, Wednesday we're going to do an activity. And then when we get back after Christmas break, you guys are going to come in and just grab model kits, and you're going to start building and playing with these and identifying angles and structures and all of that good stuff. But guys, for now, I'll put the answers up on the wall. Let's get these done. And again, we'll get them turned in on Wednesday. And again, guys, if you've got any late work, that's due before 2:45 tomorrow. So dig in, and I'll get you the answers.